Hello everyone. I'll be talking about my PhD project, which is on morphine fairing for a folding wingtip joint. So I'll just give a little bit of background on the project. It's focused on wingtip, which extends the wingspan of the wing, which helps to reduce the induced drag. But in doing so, when we increase the wingspan, it makes it larger or longer than the current width of the airport gate sizes. So we want to be able to fold the wingtip, which is why there is a hinged joint. And by changing the direction of the hinge, it allows to reduce the gust load on the wing root, which helps to reduce the weight of the wing structures. My project focuses on making a fairing to cover the joint so that there will be a smooth, compliant surface around the hinge. So I'll introduce a couple of concepts which helps us to design a fairing around this joint. So mainly the first one is that the inboard section of the wing is joined to the outboard section with a hinge joint, and on top of that we have a pivoted rib which is hinged to the joint itself. So the pivoted rib allows us to redistribute some of the deformation we get on the skin panel to the adjacent rib bay, which helps us to reduce the strain on the skin panel and also the torsional stiffness of the joint. The current work that I'm performing is mainly on modeling the deformation of the fairing. And to do that, I'm modeling the fairing as a shell surface and giving it the shell stiffness properties using an ABD matrix. The shell stiffness properties are based on a sandwich panel with a cellular core, which is shown over there. So in order to get the stiffness properties for the panel, there are a couple of approaches that I could take. Initially, I was taking an analytical approach where I was homogenizing the stiffness of the panel by using equivalent core stiffnesses and using the laminate theory to get the ABD matrix. And the current work that I'm working on is looking at using an FEA-based homogenization for the unit cell in order to get the equivalent shell stiffness matrix. But at the moment, I do not have a shell transverse shear matrix for the panel, but that would be something which would be important for a thick shell section. So that's something that I'm working on at the moment. So using the modeling framework we have developed, we are able to look at the torque response and the curvature response of the panel so that we can see if the panel is helping in reducing the torque and also in maintaining the cross-section shape of the fairing. And we are able to do parametric studies where we are varying different geometric properties of the panel itself and also the fairing to see what effect it has on the behavior. One of the more interesting results we got was we are able to increase the pre-strain across the hinge and that gives that reduces the torsional stiffness of the joint. At the same time, it also extends the linear region of the torque response. And the two animations over there shows the curvature response for different pre-strains. So in the future work, the aim of this simulation is to try and minimize the distortion of the cross-section shape. And one of the concepts that we are exploring is to spatially vary the orientation of the cellular core in the panel itself to align with some of the field variables or a metric based on field variables in order to minimize the distortion of the cross-section shape and minimize torque. Thank you.